On July 30, 2012, 600 million people across India lost power in a single night. The grid collapsed rippled outward instantly. Trains froze dead mid-route, and hospitals scrambled to keep life support running on diesel generators. 700 meters underground, 200 miners were trapped in the heat and dark as ventilation systems died. We usually think of money as the primary driver of a nation, but capital is really just an accounting system. The actual currency of growth, the physical mechanism that turns iron ore into steel or raw code into a functioning application, is energy. Historically, every superpower secured energy before it scaled. The British Empire used domestic coal to fuel the industries that eventually covered the globe. Similarly, the United States spent the 20th century securing oil fields to power its manufacturing and global logistics. The cost of missing these transitions is measurable. Between 1750 and 1900, as the West moved to coal, India's share of global industrial output plummeted from 25% to just 2%. Without a foundational, reliable power source, a nation's economic influence inevitably erodes. India's structural vulnerability comes from missing the historical energy rush. It currently imports 89 built in a remote salt desert. It is a 30-gigawatt facility designed to act as a national power bank, covering an area 5 times the size of Paris. Converting desert sunlight into reliable power is an engineering struggle. Massive solar projects in the Mojave and Sahara have previously collapsed due to the extreme environments and unsustainable economics of the desert. The Kutch Desert is particularly hostile. Summer temperatures exceed 50 degrees Celsius. The soil is hyper-corrosive with salt, and high winds constantly coat everything in a layer of efficiency-killing dust. To survive, the project uses specialized hardware. These panels are double-sided to catch light reflected from the sand, and they sit on algorithmic hinges that actively track the sun's path to maximize every minute of exposure. Because a single millimeter of dust can drop efficiency by 30%, maintenance is constant. But washing millions of panels would waste 1.7 billion liters of water a year. Instead, self-charging robots use waterless brushes to sweep the arrays every few minutes. Standard steel foundations would be eaten away by the salt in the ground. Instead, engineers drilled deep stone columns into the sand to create a stable, corrosion-resistant exoskeleton for the facility. An AI control center manages the grid by predicting weather shifts 15 minutes into the future. If the system detects a drop in sunlight, it can instantly spool up these massive 5.2 megawatt wind turbines to maintain a stable power supply. By integrating self-cleaning robotics, corrosion-resistant foundations, and predictive AI, the project addresses the specific environmental failures that have stalled previous attempts at large-scale desert power. However, building a high-tech energy park doesn't provide true independence if every solar cell and turbine blade is employed for foreign power. That simply trades oil dependency for hardware dependency. This is why the Adani Mundra facility is the critical second half of the project. It is a manufacturing hub designed to control the entire supply chain, from slicing raw silicone ingots to assembling finished wind turbines. The economic shift is already visible. Domestic solar manufacturing is seeing a 12-fold jump in capacity, and as a result, foreign expenditures for solar imports are being cut in half. True innovation comes from owning the feedback loop. By manufacturing, testing, and iterating on their own soil, engineers can identify a problem in the Kavda Desert and implement a hardware fix in the Mundra factory in a matter of days. By pairing the brutal testing ground of the desert with its own industrial factories, India is moving from a global consumer of energy technology to a foundational innovator for the next century.